Hello, this is Professor Roman. Let us continue the lecture series on linear algebra. We have been discussing the primary cyclic decomposition of an operator module and the elementary divisors that go along with it. There is an alternative decomposition to the primary cyclic decomposition, and it is called the invariant factor decomposition of an operator module. We can get that decomposition from the primary cyclic decomposition, but the invariant factor decomposition actually has some advantages over the primary cyclic decomposition. The key to this alternative decomposition is that cyclic subspaces that have relatively prime minimal polynomials can be pieced together to form another cyclic submodule. It will not be primary, but it will be cyclic. To do this, we need a preliminary result. Let tau be a linear operator, and let us have two cyclic submodules generated by u and v. And let p of x be a polynomial. Now, if p of x is relatively prime to the minimal polynomial of the first cyclic submodule here, then we can multiply the generator u by p of x and it still generates. In symbols, we have this. Okay. Also, if the minimal polynomials of the two cyclic submodules are relatively prime, we can combine those cyclic submodules into a single cyclic submodule generated by the sum u plus v. And the minimal polynomial of this larger cyclic submodule is the product of the minimal polynomials of each of the individual summands. You can see here how we're potentially losing the primariness of the summands when we do this combination. These two have relatively prime minimal polynomials, therefore they're not powers of the same prime, and so this will involve two different primes. As to the proof for part one, it's certainly clear that this submodule is contained in this one. And since we have relatively prime polynomials, it's time to use Bezo's identity. P of x and the minimal polynomial are relatively prime, so there's an equation of this form, which means that the generator u, since it's annihilated by the minimal polynomial, is equal to a of x, p of x, u, and that belongs here. And therefore we have the reverse inclusion, and so we have equality. And that's the proof of part one. For part two, first we want to show that these are essentially disjoint. If w is a vector in their intersection, it is annihilated by both minimal polynomials, and these are relatively prime, and therefore by an argument we've used before, w has to be the zero vector, and so these are essentially disjoint. As far as the direct sum, why is the sum direct? It's certainly clear that, as far as the equality here for the direct sum, it's certainly clear that we have this inclusion. U plus v belongs to this, and therefore the submodule generated by u plus v belongs here. Moreover, from part one, we can write that we know that if we take u and multiply it by the minimal polynomial of tau restricted to the other cyclic submodule, that's relatively prime to the minimal polynomial of u, then this still generates. So we get this equality. That's from part 1. We can always toss in v because this minimal polynomial annihilates v. And now this belongs in this cyclic submodule. So we have this cyclic submodule is contained in this one. Similarly, the cyclic submodule generated by v is contained in here. And so the direct sum is contained. That's the reverse inclusion. And so we get equality. Finally, as to the minimal polynomial of tau restricted to this direct sum, which is now we know the same as this, because these two cyclic submodules are tau invariant, that's what it means to be a submodule, this direct sum, they're tau invariant subspaces of this direct sum. We had a theorem back in chapter 7 that says that, therefore, the minimal polynomial of this cyclic submodule divides the minimal polynomial of this one. And similarly, the minimal polynomial of this submodule divides the minimal polynomial of this. You can't expect, of course, to remember what theorem 7.18 was, so you could search back and try to find it, but frankly, this is an argument you should be able to reproduce yourself without having to refer to an earlier theorem. In any case, because these two polynomials are relatively prime, and they divide this polynomial, their product also divides it. However, this product does annihilate this module, and so this product is divisible by the minimal polynomial of this module, the direct sum. So we have equality here. We have divisibility in both directions, and all the polynomials are monic, and therefore they must be equal. With that preliminary result out of the way, we can derive the invariant factor decomposition. Here is, we'll do it by example, because I think it'll make it quite clear how the process goes. Here is the primary cyclic decomposition of an operator module. I use brackets here to group things together based on the base polynomial, p1 of x, p2 of x, p3 of x, in the prime factorization of the minimal polynomial. So this is just what we've done before. I just grouped it to show clearly, and I added the minimal polynomials, the elementary divisors, so you could see clearly what's going on. This is what we do. For each base polynomial, p1, p2, and p3, we write out the elementary divisors in row format. Actually, for the first time you do this, you can make it a little clearer if we toss in the actual cyclic submodules that have those minimal polynomials. Now, what we do is we take the product of the polynomials in each column. So d1 of x is the product of these three, d2 of x is the product of these two, d3 of x is just this. These are called the invariant factors for tau, or v sub tau. And you'll notice by the way these are constructed, since if we look at a given row, each polynomial is divisible by by any following polynomial in that row, just powers of the same base polynomial, but no bigger powers. D3, the third invariant factor, divides the second, which divides the first. Now, we can easily, at least in theory, recover the elementary divisors from the invariant factors. All we have to do is factor each invariant factor. Therefore, knowing the invariant factors is equivalent to knowing the elementary divisors. Of course, in practice, it's a different problem. Going from elementary divisors to invariant factors is straightforward. You multiply. Going in the other direction may in fact be impossible because you have to factor. But in any case, we know that the invariant factors then are also a similarity and complete similarity invariant. And again, this is a multi-set. It's possible that two invariant factors are the same. Now, the theorem we just discussed, the preliminary result, tells us we can piece together corresponding primary cyclic submodules in an analogous way that we piece together the elementary divisors. So what we do is we reorder the summands in this direct sum by picking out the first one in each group that corresponds to this first column. And we take then the submodules generated by V11, V21, and V31. And you can see I have placed those right here, grouped them together. So the second group is from the second column here, or in this table, the second column, so it's V12, V32, so that's right here. And then the third group comes from the third column, and it's just V33 all by itself. Okay? So this table makes it easy to see how to regroup. We regroup by columns, just as we did to form the invariant factors from the elementary divisors. Now we can apply our previous theorem. Because the minimal polynomials here are pairwise relatively prime, the result we proved in theorem 941 generalizes to more than two polynomials. And we can write this as a single cyclic submodule generated by the sum of the three generators. This one is the same as this, and here we just reproduce. The minimal polynomials now, according to theorem 941, are the invariant factors. These summands, as is obvious, are cyclic, but as I said before, they're not in general primary. This last one is, of course, but the others are not. So we have a cyclic decomposition, but we do not have a primary decomposition. The invariant factor decomposition is usually far more compact than the primary cyclic decomposition, as you can tell, because we are combining cyclic submodules. But it has another important advantage. And I'm going to hold off discussion of that until we discuss the rational canonical form coming up soon, but not in this lecture probably. Basically, the invariant factors of a matrix or an operator, doesn't matter, are polynomials over the smallest subfield of the base field that contains the entries of the matrix. So in other words, the invariant factors are field independent, or what you might call field invariant. They don't vary if you raise the base field. That's why they're called invariant factors. We're also going to see that the invariant factors can be produced by algorithm that does not require factoring nasty polynomials. So the invariant factors are computable, whereas the elementary divisors are not necessarily computable. Depends on whether you can do the factorizations. So this is the invariant factor decomposition. We have an operator module with these invariant factors. The multiset of invariant factors is a complete similarity invariant, and here is the decomposition into cyclic submodules whose minimal polynomials are the invariant factors. Let's do an example. If the prime factorization of the minimal polynomial of a certain 6 by 6 matrix looks like this, and the elementary divisors look like this. This is just we're just doing an example here. Then this is what the primary cyclic decomposition looks like with 4 elementary divisors. Those are the minimal polynomials. There are 2 invariant factors. These two would be in the first column, and these 2 would be in the second column of the table we constructed. So this is one invariant factor, and this is the other. And as I glance over this, I see they are the same. Okay. The corresponding invariant factor decomposition looks like this. Well, I guess I lied earlier. It is time to look at the rational canonical form. So, suppose we have a finite dimensional operator module with minimal polynomial whose monic prime factorization looks like this. We have seen that the matrix representation of each primary cyclic summand in the primary cyclic decomposition of v tau with respect to the tau cyclic basis is a companion matrix. It's the companion matrix of the minimal polynomial for the cyclic summand. Okay. We can use these companion matrix representations to construct a matrix representation for the module or for the operator tau, and that is going to be the rational canonical form of the operator. So all we have to do is note that since the primary cyclic decomposition is a reduction of tau, we can combine the individual tau cyclic bases into a large ordered basis for the entire operator module, something we called the elementary divisor ordered basis earlier in the lectures. And under that basis, the matrix representation of tau is block diagonal, and the diagonal blocks are the companion matrices of the elementary divisors. That's quite a mouthful. You may have to review what I just did a couple of times, what I just said. In any case, this is the matrix representation of tau with respect to the elementary divisor basis since this takes up a lot of space, oftentimes you will see this written more compactly using this notation. From an invariant factor point of view, Theorem 939 implies that we can collect the companion matrices associated with distinct prime factors of the minimal polynomial. So we can collect the companion matrices that would construct that are associated with the elementary divisors. And if these are the elementary divisors, then when we combine the corresponding companion matrices, we get a single companion matrix of an invariant factor. So this is the matrix representation that would occur by combining the appropriate companion matrices. So we have two generally distinct matrix representations of the operator tau. Well, now we could use some terminology, but unfortunately there's a little bit of inconsistency in the literature. Both of these are referred to as a rational canonical form for the operator tau. So I added a little bit of notation to that, a little bit of terminology to disambiguate in this case. So here's the terminology that I'm using. This first matrix, where the blocks are the companion matrices of the elementary divisors, I will simply call the ED rational canonical form. And the other matrix here, where the diagonal blocks are companion matrices of the invariant factors, I will just call an IF rational canonical form. So a simple change in terminology to avoid any possible confusion. Okay. So both of these canonical forms, the ED and the IF rational canonical forms, are indeed canonical forms for similarity. The reason, of course, is that it's quite clear that knowing the multiset of elementary divisors is exactly the same as knowing this matrix, because the elementary divisors are simply displayed here in the last column of each of these companion matrices, and similarly knowing the multiset of invariant factors is the same as knowing the IF rational canonical form. So these two canonical forms are just simply ways of displaying, if you want, either the elementary divisors or the invariant factors. It's a packaging of those multisets into matrix form. Before looking at an example, this is the theorem, by the way, just a summary of what we've just talked about. Before looking at an example, though, there is an important corollary here. The characteristic polynomial of a matrix is the product of its elementary divisors or of its invariant factors, including their multiplicities. This follows from, if we go back to the matrices here, an earlier result that, first of all, the determinant of a block diagonal matrix is the product of the determinants of each diagonal block. And second, we know how to compute the characteristic polynomial of each of these companion matrices. We did that before. Remember, companion matrices are non-derogatory. Also, if lambda is an eigenvalue of a matrix, or operator as well, A, and if the companion matrices in the rational canonical form, this would be the ED rational canonical form, are these companion matrices, then the algebraic multiplicity of lambda is the sum of the sizes of the companion matrices. So again, I'll go back to this picture. If say P1 of x is linear, x minus lambda, then the algebraic multiplicity of lambda is the sum of the sizes of these blocks. The geometric multiplicity is the number of blocks. Remember, we know that the geometric multiplicity is always less than or equal to the algebraic multiplicity. Once we've proven the statements I just gave you, that will be obvious from this. The number here of blocks is less than or equal to the sum of the sizes of the blocks. Okay. So, why is this true? I already mentioned why the proof of part 1 is true. As for part 2a, the characteristic polynomial is the product of the elementary divisors, and so it will look like this, where this is the product of the let me get this page back here. It's the product of these polynomials here times the product of the other elementary divisors, which are relatively prime to x minus lambda. So we get this expression, and q of x is not divisible by x minus lambda. It's relatively prime to x minus lambda. So the algebraic multiplicity of lambda, which is the multiplicity of lambda as a root of this polynomial, is precisely this exponent, which is the sum of the sizes of the companion matrices. As for the geometric multiplicity, we have to dig back to some results we proved earlier in this chapter. Theorem 9.37 tells us that the primary cyclic submodule, that each primary cyclic submodule associated with the primary summand contributes a single one-dimensional subspace of eigenvectors for lambda. That actually we had to actually dig back even farther, back to theorem, it was I think 9.3. So I'm going to let you think about this, dig back through the material and get this sorted out, because I think that would be good practice. Okay. Let's take a look at an example. Here's a linear operator on R7, and we'll suppose that this is its minimal polynomial. Then, of course, each prime power factor is an elementary divisor, but the sum of the degrees of the elementary divisors has to be 7, and so we've got these two possibilities. We've done examples like this before, and they would correspond to these two rational canonical forms. Okay, it's just a matter of taking each of these and there's 3 of them here, and constructing 3 companion matrices. Okay, the last one, for example, remember how you do that. Since it's monic, you ignore the first term. You take the negatives of the other coefficients, and you set them down in the last column. Okay. As far as invariant factors are concerned, each of these multisets of elementary divisors produce multisets of invariant factors, and I multiplied them out here for you, and again you would form the companion matrices, this time of the invariant factors, and you will get 2 possibilities that look like this. So these are these 2 are the ED rational canonical forms, the elementary divisor versions of the rational canonical form. These are the invariant factor versions of the rational canonical form. Okay. And I'm saying the rational canonical form. Most people do, even though that's not quite accurate, because any reordering of these would also give you a rational canonical form. You can reorder the blocks. In this particular example, if we knew the characteristic polynomial of the matrix as well, which of course is easy to compute, then we could tell which of the 2 possibilities was the case. 2 possibilities for the invariant factor, for the elementary divisors or the invariant factors. Okay. And I'll let you ponder that. It's a result of the fact that the characteristic polynomial is the product of the elementary divisors or invariant factors, so that limits the possibilities. Well, the rational canonical form in either version is something we have sought for quite some time. It's a canonical form for matrix similarity. That's a major achievement, but unfortunately it's far from the ideal of simplicity that we had in mind for a set of canonical forms. This kind of makes the rational canonical form more of a theoretical tool than a practical one. For example, the rational canonical form exposes the connection between the elementary divisors or the invariant factors and its characteristic polynomial. This is a key fact. But still, it's these things are of somewhat limited value, certainly in a practical basis, very little value in general. This, however, is an example of the theoretical value of the rational canonical form, and I'm going to leave the proof here as an exercise. Square matrix A is similar to its transpose, and I'll let you think about that. The proof without using rational canonical form would be much more tedious, so that's something to think about. Let's conclude this lecture by explaining why the invariant factors are really invariant. On several occasions, we've considered a real matrix to be a complex matrix that happens to have real coefficients. And we have seen that neither the minimal polynomial nor the characteristic polynomial is affected by a change of base field, an upgrading of the base field. What about the elementary divisors and the invariant factors? Well, let's consider an example. Suppose that the minimal polynomial of a real matrix, size 8 by 8, looks like this. and the elementary divisors are these. So this base polynomial x squared plus 4 has 2 elementary divisors, and x squared plus 9 has just a single one. These are the invariant factors. I'm sorry, these are the elementary divisors. These are the invariant factors. Okay. A little parentheses missing. As a real matrix, then A has this ED rational canonical form. These are the companion matrices of the elementary divisors. But as a complex matrix, the minimal polynomial factors further, as you would expect in general, and we have seen that, we talked about this just a few minutes ago, that we can combine or split companion matrices. So we can combine these two companion matrices because these two polynomials are relatively prime to a single companion matrix associated with the product. So in reverse, because the minimal polynomial splits or factors further over the complex field, the companion matrices can be split, and our complex ED rational canonical form now looks like this. So it is quite different. The elementary divisors are different, and the ED rational canonical form is different when we upgrade from the real field to the complex field. Here are the elementary divisors in here. But what about the invariant factors? Well, we gather together the first companion matrix of each type. So here, this one and this one correspond to x plus 2i, x minus 2i, x plus I, x minus I. So these we would skip because they're the same base polynomial here, but here we pick up these two, so we get 1, 2, 3, 4. When we multiply these two together, we get this guy. When we multiply these two together, we get this guy. This product here is then one of the invariant factors that's sitting right here. Okay, these are the same as we had before. The elementary divisors have changed. The invariant factors have not changed. We can see this a little more clearly. To prove this in general is a little messy notation and so on, but let's do an example that's not specific like we just did, and you'll see what's going on and why it generalizes. Okay, so suppose that the elementary divisors of a matrix looked like this in row format. This is the table we've constructed before, but I didn't put it in a grid with column heading, with row headings. Okay, so P1 of x is one of the base primes, occurs to 2 powers, P2 of x and P3 of x. Okay. Now, suppose that in a larger field, the complex field, P1 split into a product Q1, R1. What happens to the elementary divisors as viewed as a complex matrix? Well, P1 cubed of x, the first real elementary divisor, splits into 2 complex elementary divisors, and same thing for the lesser power of P1. So that first row in this table gets split into two rows. So there is a definite change in the elementary divisors. But the column products are not affected. In other words, the invariant factors are not affected, because when you take the product of this, the polynomials in this column, the product of the first two give you back P1 of x cubed. So you get exactly the same invariant factors as you did before. You get different elementary divisors, but the same invariant factors. Okay? So that is why the invariant factors do not depend on the base field, whereas the elementary divisors do.